There's something extraordinary happening in our solar system right now. Something that has captured the attention of astronomers worldwide and sparked debates that range from scientific curiosity to wild speculation. We call it 3I/Atlas, but that name doesn't even begin to capture how strange this visitor truly is. Imagine an object traveling through the cosmic void for billions of years, moving at speeds that dwarf even our fastest spacecraft, carrying secrets from a star system we may never identify. This isn't science fiction. This is happening right now, and every day we're learning something new that challenges what we thought we knew about the universe. I'm going to take you on a journey through one of the most fascinating astronomical discoveries of our time. We'll explore what makes 3I Atlas so unique, dive into the cutting-edge research that's revealing its secrets, and yes, we'll even address the elephant in the room, the alien theories that have captivated public imagination. But more importantly, we'll separate fact from fiction and show you what science is actually telling us about this incredible cosmic wanderer. Chapter 1. The Discovery. Let's start at the beginning. On July 1st, 2025, astronomers working with the ATLAS survey system, that's the Asteroid Terrestrial Impact Last Alert System, made a routine observation from their telescope in Rio Hurtado, Chile. They spotted what they initially thought was just another asteroid, another piece of space rock drifting through our solar system. But within hours, they realized they had found something extraordinary. The object was moving fast, really fast. To understand just how fast, let me give you some perspective. Earth orbits the Sun at about 30 kilometers per second. That's already incredibly fast. You could circle the entire planet in about 20 minutes at that speed. Mercury, being much closer to the Sun, has to move even faster to maintain its orbit, about 48 kilometers per second. But this new object? It was clocking in at 58 kilometers per second, and it was still way out near Jupiter's orbit. That speed told astronomers something crucial. This object wasn't from around here. It was moving so fast that the Sun's gravity couldn't capture it. This was an interstellar visitor, only the third ever detected, hence the name 3I, Third Interstellar Object, combined with ATLAS, the survey that found it. But here's where the story gets interesting. While ATLAS officially discovered 3I ATLS on July 1st, the object had actually been captured in images much earlier. Researchers working with NASA's TESS mission, the Transiting Exoplanet Survey Satellite, realized they had data on his comet dating all the way back to May 7th. For nearly a month, from May 7th to June 2nd, TESS had unknowingly been photographing our mysterious visitor as it journeyed through the outer solar system. This wasn't just a lucky break. This early data would prove invaluable for understanding 3I ATLS's behavior and characteristics. It gave scientists a longer timeline to work with, more data points to analyze, and ultimately more questions to answer. Chapter 2. Not Your Average Comet. Once astronomers confirmed they were dealing with an interstellar object, the real work began. Every major telescope that could be pointed at 3I ATLS was mobilized. And what they found was, to put it mildly, weird. First, let's talk about what we expected. When you hear interstellar comet, you might think of something like 2I Borisov, the second interstellar object ever discovered back in 2019. Borisov was actually pretty normal. Aside from the fact that it came from another star system, it behaved like any other comet we'd seen. It had a coma, that fuzzy cloud of gas and dust, and a tail, and it brightened as it got closer to the Sun. Scientists could predict its behavior because it followed the rules we understood. 3I ATLS decided to throw the rulebook out the window. Let's start with its brightness. When researchers analyzed the test data from May and June, They calculated that as the comet moved about 1 astronomical unit closer to the sun, its brightness should increase by a factor of 1.5. That's just basic physics. Get closer to a light source, reflect more light. But when they actually measured the change, they found the brightness had increased by a factor of 5. Not 1.5, but 5 times brighter than expected. This massive surge in brightness told astronomers something important. 3I ATLS was incredibly active. It was already forming a substantial coma of gas and dust, and it was doing this at a distance where most comets would still be frozen solid. Remember, this was happening when the comet was still beyond Jupiter's orbit, more than 5 astronomical units from the sun. At that distance, it's cold, really cold. Most comets don't start actively outgassing until they're between 3 and 4 AU from the sun. So why was 3I ATLS so active so early? The answer lies in its composition, and this is where things get really interesting. Chapter 3: The Chemistry of an Alien World. When powerful telescopes like the James Webb Space Telescope and the Hubble Space Telescope turned their attention to 3I ATLS, they began to unravel its chemical secrets. And those secrets revealed a comet unlike anything we'd seen before. On August 6th, scientists used JWST's near-infrared spectrograph to analyze the composition of 3I ATLS's coma. What they found was surprising. The comet was releasing far more carbon dioxide and carbon monoxide than water. In a typical comet from our solar system, water ice dominates the composition. When these comets get close to the sun, they release massive amounts of water vapor, along with some CO2 and other gases. But the ratio is heavily weighted toward water. 3I ATLS was doing the opposite. The ratio of carbon dioxide to water was about 8 to 1. Imagine a comet that's essentially made of dry ice rather than regular ice. This explains why it became active so early and so far from the sun. Carbon dioxide doesn't need much heat to sublimate. That's the process where a solid turns directly into a gas without becoming liquid first. You've seen this if you've ever watched dry ice create that spooky fog effect. That's CO2 sublimating at room temperature. This high concentration of carbon dioxide had another effect. It was actually launching dust particles away from the comet's nucleus with considerable force. The researchers found dust emanating from the comet in the direction of the sun, which is unusual because typically a comet's tail points away from the sun, blown back by solar wind. But the excessive CO2 production was so vigorous that it was pushing material in all directions, including sunward. But the chemical surprises didn't stop there. As 3I ATLS continued its journey closer to the sun, astronomers detected something that really shouldn't have been there: metal, specifically nickel. Now, finding metal in a comet isn't entirely unprecedented. Many comets contain trace amounts of various metals in their composition. But here's the thing. Metals only typically start vaporizing from comets when they get very close to the sun, where temperatures are high enough to actually vaporize metal. 3I ATLS was releasing nickel when it was still between Mars and Jupiter, where it's far too cold for that to happen naturally. And here's another odd detail. Initially, they detected nickel, but no iron. Nickel and iron are typically found together because they're both formed in the cores of dying stars and get distributed together when those stars explode. Finding one without the other is unusual. It wasn't until later observations in September that iron finally started showing up in the coma and the ratio normalized to what we'd expect. The presence of these metals, particularly the unusual nickel-to-iron ratio, sparked all kinds of speculation. Some people pointed out that rocket engines use nickel-rich alloys, and burning rocket fuel produces both CO2 and nickel in the exhaust. Could this be evidence of propulsion? We'll get to that theory later, but let's just say the scientific explanation is far more mundane, even if we don't fully understand it yet. Comets tend to scatter light in a peculiar way. The light tends to be perpendicular to this plane, which we call positive polarization, or parallel to it, which is negative polarization. Most objects in space, including most comets and even 2I Borisov, show positive polarization. 3I Atlas shows negative polarization. Not just negative, but what researchers called exceptionally deep and narrow negative polarization. This is a pattern that had never been observed before in any comet or asteroid from our solar system. On September 5th, a team led by researcher Zuri Gray published the first ever polarimetric observations of 3I Atlas. They used data from telescopes in Chile, the Canary Islands, and Bulgaria, and what they found was unprecedented. The way 3I Atlas scatters light is so unique that it might represent an entirely new class of small planetary bodies. Think about what this means. We've observed thousands of comets and asteroids in our solar system. We've studied them for centuries, and now an object from another star system arrives and shows us a light-scattering behavior we've never seen before. It's like discovering a new primary color. The closest analogs scientists could find were some trans-Neptunian objects and centaurs, those strange bodies in the outer reaches of our solar system. But even those aren't perfect matches. 3I Atlas stands alone in its light polarization characteristics, a reminder that other star systems may produce objects with properties we've never encountered. Chapter 6. Size Matters. When 3I Atlas was first discovered, early estimates put its nucleus, the actual solid body at the center of all that gas and dust, at around 10 kilometers in diameter. That would make it substantially larger than both Oumuamua, which was maybe 400 meters across, and 2I Borisov, which was about a kilometer wide. But those initial estimates had a problem. They were based on the assumption that all the light we were seeing was being reflected from the nucleus itself. In reality, much of that light was coming from the coma, the cloud of gas and dust surrounding the nucleus. It's like trying to judge the size of a light bulb from looking at a lampshade from across the room. Enter the Hubble Space Telescope. Getting time on Hubble is notoriously difficult. Scientists have to submit proposals months in advance, competing for every precious minute of observation time. But Hubble reserves some time for targets of opportunity, unexpected events or objects that need to be observed before they disappear. 3I Atlas definitely qualified. On July 21st, when 3I Atlas was about 446 million kilometers from Earth, Hubble captured detailed images of the comet. You can actually see the comet's incredible speed in these images. The background stars appear as streaks because of how fast 3I Atlas was moving relative to them. The images also beautifully showed the teardrop shape of dust streaming off the icy nucleus. But most importantly, these observations allowed scientists to separate the light from the nucleus from the light scattered by the coma. The result? 3I ATTLAS's nucleus is actually much smaller than initially thought, somewhere between 440 meters and 5.6 kilometers in diameter. The most likely estimate puts it around the upper end of that range, but still significantly smaller than those initial 10-kilometer estimates. This size revision is important for several reasons. First, it affects our calculations about how much material the comet is releasing and how active it really is. A smaller nucleus outgassing at the same rate means the comet is even more active relative to its size than we thought. Second, it influences our understanding of how common such objects might be in interstellar space. And third, it directly challenges some of the more speculative theories about 3I ATTLAS, but we'll get to those shortly. Chapter 7. The Peculiar Path. Let's talk about how 3I ATTLAS moves, because this is where things get really interesting and, admittedly, a bit strange. When a comet heats up as it approaches the sun, ice on its surface sublimated, turning directly from solid to gas. This release of gas acts like tiny rocket thrusters, pushing the comet around in space. Scientists call this non-gravitational acceleration, or NGA. It's completely normal and expected. In fact, measuring these small changes in trajectory helps scientists understand what a comet is made of and how vigorously it's outgassing. Here's where 3I ATTLAS breaks from the norm. Despite showing clear signs of active outgassing, remember that factor of 5 increase in brightness, the substantial coma, the unusual dust behavior, 3I ATTLAS has maintained an almost perfectly steady trajectory. Between May and October, as it traveled from beyond Jupiter's orbit toward its closest approach to the Sun, its velocity and direction fluctuated by only about 1.5 kilometers of NGA per day. Let me put that in perspective. 2I Borisov, which was actually pretty typical for a comet, showed variations of over 100 kilometers per day. Comet Hale-Bopp, one of the largest comets ever observed, varied by more than 10 kilometers per day. And Oumuamua, it was all over the place, with variations exceeding 1,000 kilometers per day at some points. 3I ATTLAS is holding a course that's steady to a degree we've never seen before in an active comet, as if it's immune to the random pushes and pulls that normally buffet these icy bodies as they heat up and release gas. Now, there are potential natural explanations for this. Perhaps the comet is rotating in such a way that the outgassing is perfectly balanced, with jets firing in opposite directions that cancel each other out. Perhaps its shape or composition creates a symmetry in how it releases material. These are questions that require more research and observation to answer. But you can see why the steady trajectory has raised eyebrows. A course so precise that it barely deviates despite active outgassing. It's unusual enough to warrant serious scientific investigation, even if the explanation turns out to be entirely natural. And there's another aspect to 3I ATLS's trajectory that's worth noting: its alignment with the solar system. Our solar system is essentially a disk of planets, asteroids, and other objects all orbiting in roughly the same plane. We call this the ecliptic plane. Pluto, famous for being weird, is tilted about 17 degrees from this plane. 3I ATLS came in at an angle of only 3 degrees from the ecliptic plane. Think about that. Space is three-dimensional. An interstellar object could approach from any angle from any direction. Yet 3I ATLS arrived almost perfectly aligned with our solar system's disk, approaching from the side, like a T-bone collision, rather than head-on like its interstellar predecessors. Space is vast and mostly empty. The probability of an object approaching so precisely aligned with our solar system's plane by pure chance is, well, it's low. Not impossible, not even improbable enough to rule out chance, but low enough to be noteworthy. Remember how I mentioned that 3I Atlas started out as a CO2-dominated comet with very little water in its coma? Well, as it got closer to the Sun, something dramatic happened. By late September, as the comet passed through the orbit of Mars at about 1.5 AU from the Sun, observatories detected a sudden and massive increase in water vapor production. We're not talking about a gradual uptick here. This was like someone turned on a fire hose. The amount of water vapor being released was actually more than scientists would expect, even from a typical solar system comet at that distance. That appeared almost overnight, transforming the comet's activity in ways that caught observers off guard. This raises fascinating questions about the comet's internal structure. Perhaps 3I Atlas has a layered composition, with a CO2-rich outer shell that sublimated first, followed by a water-rich interior that became exposed as the comet warmed up. Or maybe the heating process triggered some kind of cascading effect, where the release of CO2 created cracks and fissures that exposed fresh water ice to the sun's radiation. Whatever the mechanism, this sudden appearance of massive water vapor production is yet another way that 3I Atlas refuses to behave like a typical comet. Typical comets show gradual changes in their outgassing as they approach the Sun. 3I Atlas seems to prefer dramatic transformations. And speaking of drama, let's talk about cyanide. Yes, cyanide. On August 27th, researchers using the Gemini South telescope in Chile captured multicolored images of 3I Atlas using the Gemini multi-object spectrograph. These observations were special because they not only showed the coma, but also captured the comet's growing tail, which had become noticeably longer than in previous observations from July. But the real excitement came when astronomer Ben Yang, assistant professor at Diego Portales University, identified an emission feature in the CN band. CN stands for cyanogen, essentially cyanide molecules. The comet was releasing hydrogen cyanide. Now, before anyone panic, this is actually normal for comets. As water ice sublimates in sunlight, it releases trapped hydrogen cyanide, which then gets broken apart by solar radiation into its constituent elements. We typically start seeing this when a comet gets between 2.5 and 3 AU from the Sun, exactly where 3I Atlas was at the time. Researchers calculated that the comet was releasing about 800 sectillion cyanide molecules per second. That's 8, followed by 23 zeros. It sounds like a lot, and it is, but it's actually on the lower end of the scale for comets in our solar system. What made this interesting wasn't the presence of cyanide itself, but what it told us about the comet's carbon content. By measuring the ratio of C2, diatomic carbon, to CN, cyanide in the coma, scientists could characterize 3I Atlas's carbon chain composition. The result? 3I Atlas produces less than 0.09 C2 molecules for every CN molecule. This places it as one of the most carbon chain depleted comets ever observed. Interestingly, 2I Borisov shared this characteristic. We now have two interstellar comets, and both show carbon chain depletion compared to typical solar system comets. Is this a pattern? Do comets from other star systems tend to be carbon chain depleted? Or is this just a coincidence based on our incredibly small sample size of interstellar objects? With only two comets to compare, it's dangerous to draw broad conclusions. But it's certainly intriguing that both interstellar comets we've been able to study in detail share this unusual characteristic. This carbon chain depletion also ties back to the green glow mystery. If the comet is depleted in C2, where is the green fluorescence coming from? Some scientists speculated that perhaps C2 production ramped up significantly as the comet got closer to the Sun, which would explain both the later detection of C2 and the green appearance observed during the lunar eclipse. Chapter 10: The Tale of Two Directions. Comet tails are iconic. When most people picture a comet, they imagine a bright nucleus with a long streaming tail stretching out behind it. That tail is created by solar wind, the constant stream of charged particles flowing from the Sun, which blows the lightest particles of dust and gas away from the comet. Because solar wind flows away from the Sun, comet tails always point away from the Sun. Always. Except when they don't. When 3I/Atlas was first observed in detail back in the summer, astronomers noticed something strange. It had developed the tail pointing toward the Sun. This sun-facing tail was completely backwards from what should happen. The explanation likely relates to that early vigorous CO2 outgassing we talked about earlier, when 3I/Atlas was still far from the Sun, beyond Jupiter's orbit. It was already subliming CO2 at a rapid rate. But at that distance, the solar wind isn't particularly strong. So instead of the gas and dust being blown away to form a proper tail, it accumulated on the warm, sun-facing side of the comet. Think of it like this. Imagine you're gently blowing on a pile of feathers while someone is vigorously dumping more feathers on top. The feathers pile up faster than your gentle breath can blow them away. That's essentially what was happening with 3I/Atlas's early sun-facing tail. As the comet got closer to the Sun and the solar wind strengthened, this changed. By late August and into September, observations from the Gemini telescopes showed that 3I/Atlas had developed a proper fan-shaped tail pointing away from the Sun. The August 27th observations measured this tail at about 1/120th of a degree in the sky. significantly longer than it had appeared in July.